Now, you may have heard of the website, the Online Encyclopedia of Integer Sequences. It was started by Dr. Neil Sloan back in the 1960s, and it features sometimes in other channels like Numberphile. Now, I have been playing around with different integer sequences just in my head for fun and recreation, but I actually found a sequence which I thought would be kind of interesting for the online encyclopedia website. So I submitted it, and I'm grateful to say that it has been accepted. Now, what is an integer sequence? An integer sequence is a sequence of integers. 1, 2, 3, 4, 5 would be 1, 2, 4, 6, 8, 10 is another one. 2, 4, 8, 16, 32, 64, 128 is another one. Fibonacci sequence is one. Prime numbers is one. You know, and in fact, there are actually hundreds of thousands in the database, and of course, there are many, many more. So in this video, I want to tell you all about the sequence that I've got published in there, how it works, how you calculate it, just for fun, really. So if you want to find out more, please let me explain. Okay, so the title of my sequence is the number of distinct states before repetition for a circular array of n distinct elements under repeated adjacent XOR operations. Okay, so here is the sequence in its, well, I won't say full glory because it's would appear it's an infinite sequence, but here it is in the first few terms that we have. So we'll look at it more in detail, some of the features of this sequence in a moment. But first of all, the word XOR was used there in the title, so it's exclusive OR. So let's do a quick refresher on exclusive OR. Now, to look at exclusive OR, we'll start by looking at OR. So in normal language, we would say this or that, raining or snowing, for example. So if this is true or this is true, then we do something. So when you turn that into Boolean logic, you would get 0 or 0. So neither of them are true is 0. You don't do anything. So it's neither raining nor snowing. But in the other cases, one or the other, raining but not snowing, 1 or 0 is 1, which is true, we do something. 0 or 1, so it's not raining but it is snowing, we do something. And in fact, if it's raining and snowing, I don't know, I'm sure in some parts of the world that must be possible, 1 or 1, then you do something. So unless it's 0 and 0, everything else is a 1. So exclusive OR is very similar. So if you've got 0 XOR 0, you get 0. 1 XOR 0, you get 1. So it's the same as OR at the moment. 0 XOR 1, you get 1. But this is where the exclusive bit comes. Only one of them is allowed to be true. So exclusive, it has to be exclusively true. So if you get 1 XOR 1, you get 0. So in this case, if they're both the same, you get 0, and if they're different, you get 1. So in other words, XOR is true if exactly one of the two inputs, A or B, is true, and false if both are the same, either true or false. And you can actually write that using other logic. So it's actually A and not B, or not A and B. You can write a little Python program or a C program to try that out, and that will give you the same thing. So you can build exclusive OR logic from, in fact, OR and a not combined together. Now, I've done a whole video on the power of exclusive OR, so I won't go too much more into it now. Just to say, there's just kind of these properties, which is if you take A, and this symbol here is exclusive OR in Python, so I've used it here. A exclusive OR B gives you this answer C. But if you then take A and exclusive OR it with C, you get back to B. So this is really important. And in fact, if you take B and exclusive OR with C, you get back to A. So the point is, if we follow this example, 133 exclusive OR 88 is 221. These could be any numbers. I just picked two random numbers here. And if you take that 221 and exclusive OR it with 88, you get back to 133. So it's magic. And 221 exclusive OR with 133 gives you 88. So you have three numbers, but you only need two of them to calculate the third. And this is used for things like RAID, because it means that if you put this number onto a disk, then if either of these two disks fail, but you've still got this disk with this number, 221 on it, but the 88 disk fails, you can get back the 88 because 221 or 133 is 88. So you've now been able to rebuild the data, and that's what they do with RAID disks. It's also used for encryption because you can take a number, you can use this as the encryption key, and you get a completely different number out, and you can't work out how you got here. If you look at 221, you've got no way to know that it was 133 exclusive OR 88, because it could be any other numbers that give you 221 as an answer. Now let's get into this sequence. This is how it all kind of started, with triangles and squares. So we'll start with a triangle. So 3 sides, in other words, 3 nodes. That's what we're really talking about in a graph, and they're all connected together. So I've got 133, 101, 42. They're just random numbers. It works with any number. It doesn't matter what you put in there. Now, if I exclusive OR 133 with 101, I get 224. And if I do 101 with 42, I get 79. And if I do 133 with 42, I get 75. Okay, so I've just exclusive OR'd some numbers together and I've got their results. Now here I've also got 3 numbers. So I could build another triangle with these 3. So there you go, there's the same triangle, but I've now got my new numbers in them. So this is like round 2. I've done this once, got some numbers, and now I'm in round 2. Now watch what happens when I start exclusive ORing these ones together. 224 exclusive OR with 79 is 175. Well, that's interesting because it's this 175 is over here. 79 with 175 gives me 224. Well, that's interesting because 224 is over here. 224 with 175 is 79. Well, that's interesting. That's over here. So, in fact, I've got the same 3 numbers. I come up with the same triangle. It's shifted around a bit, but it's just, depending on your point of view, it's the same 3 numbers in the same order. Just depends on where you start. So if I exclusive OR them again, I'll still get the same 3 numbers because I've just had the same 3 numbers. So what we're actually seeing is, if you look at this in notation, you start with A, B, and C. And then A XOR B is the first operation. B XOR C is the second operation. And C XOR A, because we go back round again, is the third operation of this second round. Okay, now if you then go to the next round, what you're actually saying is A XOR B, and then you XOR it with this, XOR B XOR C. So look, A XOR B XOR B XOR C. These 2 terms exclusively ORed together. Okay, and then the others follow exactly the same pattern. But A XOR B XOR B XOR C, when you XOR something by itself, you remove it. So that can actually be reduced to A XOR C. And this can be reduced to B XOR A and C XOR B. Now, if you actually look, let's take this last one. C XOR B is actually B XOR C. It's the same thing, just the other way around, because XOR works in both directions. So if you reformat that, you get A XOR B, B XOR C, C XOR A, which is the numbers we started with, which is why you get this repetition. So logically, you can see, using symbols and things, we can work it out. So that layer is that layer, which means we didn't just get repeats. That round and that round just keep repeating round and round again. So for n of 3 nodes, distinct states before repetition is 2. After 2, you start to get a repetition. And that's the beginning of our sequence. That's how I begin to create the sequence. For n of 3, I got the answer of 2. Now, let's move it up. Let's go to 5. We're going to go back to 4 in a second, but let's go to 5 because it's interesting as well. So now I've got 5 nodes, all linked together in a closed loop. They all go round and round. And I can start to do the same operation. So I start with my original numbers, 1, 3, 3, 2, 3. Again, these are random numbers. You can put any numbers you like in there. These are just ones I picked just for illustration. So 133 XOR 234 is 111. 234 XOR 101 is 143. And you can actually just, I'm not going to keep writing XOR, I'm just going to give you the results. So there's the results of that complete round of XORs. And now we do it again. We put those numbers into our little 5 groups of numbers there, and we do it again. Okay, nothing interesting seems to be happening. We've got another set of numbers. And so we go in again and we repeat around again. And again, now we've just got another set of numbers. So at this stage, you'd think, well, this isn't very interesting. I'm just going to keep changing these numbers and I'm just going to keep getting more and more different numbers out. But in fact, if you do it one more time, look what happens. 175, 111, 143, 118, 57. Well, that's the same as that line there, just shifted along one. So it's all in the same order. Okay, 11143, and it ends in 175. Now it starts in 175 and then goes through the same order. So it's the same layer, just rotated round, because you can present that group of 5 nodes in any way that you like, as long as they are still connected to the same neighboring nodes in the same way. So here we see that for n of 5, the distinct states before repetition is 4. So now I've started to get a sequence. I did it for 3, n of 3. I did it for n of 5. Okay, and it's not the same number. I get different numbers. Now, if you want to see that again using all the symbols, it's here. I won't go into it. You can pause the screen and just go through all that logic if you want to, but it's right. Okay, so let's go back to our square. We missed over 4. Now this is an interesting, fairly unique case. 4 numbers, again, completely random. Okay, if we exclusive all them, we get these 4 numbers, again, a square. Okay, so let's start doing it in our way. There's our original numbers. There's the second round. Now watch what happens in the third round. 174244, 174244. So I've now got a repeating pattern. And again, you can do this for any numbers. You'll get a repeating pattern, not the same pattern, but you'll get this repeating pattern. And if you then go into another round, you get the same number. In this case, it's 90, but just depending on your starting numbers, you'll get different numbers, but you'll get the same number repeated 4 times. Now, we've had no repetition yet. Nothing is repeated, but we're whittling our way down to just 4 numbers now that are the same. And with XOR, if you do that, you get 0. And then XOR 0 is 0, you get 0. So now we're getting a repeat. In fact, we're getting a repeat of zeros all the time. So for n of 4, distinct stages before repetition is 5. And it turns out when n is a power of 2, then the state always reduces to 0. And again, here's the logic. You could pause that screen if you want to study it to see how it's all working. So let's go back to our little sequence here. Here we can see 2, we found that out. 5, we just found out for the square. 4, we found out for our 5 nodes, and so on and so on. Now here, that 9, this is a power of 2, and you can go along here. 17, that's a power of 2, not 17, but that the sequence number. Okay, so it gets added an extra 1 onto it because it reduces to 0, and then the 0 starts repeating. And what's interesting, you can see, 5, 4, 4, 8, 9. It looks like a fairly interesting sequence with some well-known numbers, 32, 8, 64. But then look, later on, it starts to grow. 87,000 we've got up here. Right at the end here, 536.8 million iterations are required before you get that repeat. So it's quite an interesting sequence because the more nodes you've got in that graph, the more nodes you've got in your loop of XOR numbers, you get some very big numbers. But of course, it's not really relate to the end, because look, this one's only 64. So 64, and then just 2 more later, you're up to 536 million. Okay, look, there's some other ones here, 2, 5, 6, 32 here, sandwiched by 2 very big numbers on either side. So it's not always obvious what it's going to grow. It's not going to grow bigger. It goes up and down. Now, here's an interesting thing. There's another sequence, 6519, which is the highest power of 2 dividing any number n. And here is the sequence listed for us. And what that means, if you've got n of 24, for example, 8 goes into 24, so that's fine, 2 to the power of 3. But 2 to the power of 4, 16, does not go into 24. So the highest power of 2 dividing n in this case is 8. So the a of 24 is 8. And we can see that there in the sequence here. So let's just park that. That's an interesting sequence to do with powers of 2 and dividing. Just park it for the moment. Now there's another sequence which, let's just read this. The eventual period of a single cell in a Rule 90 cellular automaton in a cyclic universe with the width of n. Okay, what does all that mean? Well, we'll talk about it, but look at this. It's similar to the sequence I've been describing, not the same. It's similar. These ones here at the beginning, they're not the same. You can see 1, 1, 1, 1. We were in 2, 4, and 5. Okay, it's different, but you can also see smaller numbers sandwiched between bigger numbers. You can see a number here, 536.8 million. Well, that seems familiar, but it's not the same number. Ours one ended in a 12, not an 11. So it's similar, but not the same. So what are we talking about here? Well, an elementary cellular automaton is a one-dimensional cellular automaton where there are 2 possible states, 0 and 1. So it's binary, like we've been dealing with. And you have a rule that determines the state of the cell in the next generation, the next round, like we've been doing. But it depends only on the neighboring cells. Now, we've got neighboring cells, but in our case, they go around in a loop. Now, Rule 90 is an elementary cellular automaton based on XOR. So the rules for the next generation is based on XOR. So this is, again, getting close to what we were doing. And in fact, this is the subject of a whole book. Okay, it's the simplest non-trivial cellular automaton as described exclusively by Stephen Wolfram of the Wolfram fame, okay, in his 2002 book, A New Kind of Science. So we're kind of dancing in this area. And you can actually create pictures from these automatons. This is the Rule 90 automaton image that I grabbed from Wikipedia. So what does it turn out? It actually turns out that if you add those 2 sequences together, you get the sequence that I've been describing using the closed loop method that I've shown you. So let's see that in action. Here are all three of them. So look, this item here is 4. This one here is 1, and you add them together and you get 5 here. Okay, let's try a different one. This one's 8. Over here, the corresponding one is 56. Well, 8 plus 56, 64. And so if you add that to that, you get my one. Or you could say another way, if you take any one of these and subtract it from my one, you're going to get the other one. So these three kind of live together, although they're very different parts of mathematics, very different ideas, although two of them are related in terms of XOR, and they come together when you join them using my sequence. Okay, there you have it. Not really much more to say. Hope you enjoyed the video. If you did, please do give it a thumbs up. If you like these kind of videos, then I invite you to stick around by subscribing to the channel. Okay, that's it. I'll see you in the next one.